As just a short recap, we were doing sigma bonds. I told you that you had covalent bonding, in which you had nonmetals, and the nonmetals would try to pull each other's electrons, which is why, uh, which is why the electrons, because both nonmetals are electronegative, they're trying to pull the electrons. So the electrons are going to get stuck in the middle. This wants one electron, this wants one electron, so the two electrons are stuck in the middle. That was what a covalent bond was. And at the orbital level, this is represented by overlapping orbitals. Like if you've got a hydrogen atom, it's got an electron in the s orbital. The other hydrogen atom also has an electron in the s orbital. So there's one electron, negative charge in this spherical region, the negative charge of one electron in this spherical region. They both try to gain those electrons. They try to pull each other's electrons. So the two electrons are now stuck in the middle. So the new orbital, bonding orbital, would be this one. The two orbitals would merge. They're going to mix up, and the two electrons will be stuck in the middle, and that's your sigma bond. The electron density lies right in the middle. And similarly, you had an S and P overlap. These orbitals could also overlap. And the example for that was, you must know how to draw these. They're going to ask you for this. So there was an S and P overlap. So hydrogen atom and fluorine atom. Fluorine has one electron missing in its last orbital, which is 2pz. So here's your p orbital of fluorine. The nucleus of fluorine is the middle. And here's your hydrogen, and that's got one electron as well. Again, the two atoms, they try to gain each other's electrons. The electrons are stuck in the middle. And the end result is the electron density would be maximum in this middle area over here. The electron would kind of stop going to the other side. Okay, that's fine, Mikhail. So the electron,
thank you, sir.
So the electron would kind of stop going to the other side. That side would shrink, and this lobe over here, the two lobes would mix up, merge up, and the two electrons are going to be found in the middle area. And similarly, you had a p and p overlap. You got two fluorine atoms. P orbital needs one electron of fluorine. The other orbitals are all full, so I don't care about them. So fluorine has one orbital that needs an electron. The other fluorine also has one orbital that needs an electron. So they start fighting over those electrons. The electrons are stuck in the middle. So the middle part, its charge density or its probability would increase. There's going to be a much greater, higher chances of the electrons to be found in this middle part, and these sides would shrink. And that's another type of sigma bond. So we did all these types of sigma bonds, and I showed you that atoms can form multiple sigma bonds. Like we did the water molecule. Now in a water molecule, if you look at oxygen's electrons, all the other orbitals are full. Oxygen has two orbitals that need electron. So there's a 2py and there's a 2pz. So let's call this the 2py, the blue one. That's the 2pz. They both need electrons. So they try to pull hydrogen's electrons. So hydrogen comes in, another hydrogen comes in with its spherical orbital, and they try to gain those electrons. The end result is they won't be able to gain those electrons because both atoms are equally or have almost the same electronegativity difference. So the electrons get stuck in this middle part. And if I show this properly, you'll be finding the two electrons somewhere in this middle space over here. The two electrons over here would also, that's two sigma bonds. So this is the last thing that we did. And we talked about sigma bonds. I told you that sigma bonds, it's an end-to-end overlap of orbitals. It's a sharing of electrons where the orbitals kind of mix up. They merge and they end-to-end overlap. The electron density lies exactly in the middle on the axis connecting the two nuclei. And we're not going to talk about rotation yet. But the fourth point is important, that every atom, the first bond is going to be a sigma. Whenever two atoms bond together, the first bond is going to be a sigma. If they end up forming a double bond, then the second bond would be a pi bond. If they end up forming a triple bond, then the other two would be pi bonds. So we're going to do examples of pi bonds now. Now, So let's do a couple of examples of how pi bonds are going to be formed. So the first thing is I'm going to write down the properties of pi bonds later. So first, let me explain what a pi bond is. So the pi bond, remember, the first bond between atoms is always a sigma. If you have a double bond or you have a triple bond between atoms, the first bond would still be a sigma. The next one would be a pi, and the same is the scenario. So when you're looking for pi bonds, you're basically looking for double bonds or triple bonds. That's where you're going to find pi bonds. So it's going to be 1 sigma plus 2 pi. So the example is that we're going to look for molecules where there's a double bond. So one simple example is an oxygen molecule. It's an O2 molecule. In an O2 molecule, the oxygen has a double bond with another oxygen atom. So they're forming double bonds. And if they're forming double bonds, let's write the electronic configuration of oxygen. Like oxygen's electronic configuration is 8 electrons. So that's again 1s2, 2s2. So all the other orbitals are full. 2p4, so that means 2py is 1 and 2pz is 1. So oxygen needs electrons in these last two. It needs electrons in the last two orbitals. So I'm going to draw these two oxygen atoms. I'm not going to draw the other orbitals because they're already full. They're not involved in bonding. So let's draw these two orbitals. Here's your oxygen nucleus. And so that is one of the orbitals of oxygen. It has at the moment just 1 electron. And remember, the negative charge of that 1 electron is going to be distributed in the entire, let's call that the 2py orbital, and it's got 1 electron. And then there's another oxygen atom. Sorry, there's the same oxygen, but another orbital of oxygen. And that's got 1 electron that's buzzing in the 2p. Let's call that the 2pz orbital of oxygen. So there's 1 electron in that as well. So there's this 1 electron that's buzzing in the so there's 1 electron that is kind of buzzing in on this axis. So oxygen has 2 orbitals that need electrons. It needs an electron in this one, it needs an electron in this one. Now what's going to happen is that there's going to be another oxygen which is going to be exactly the same, having the same electronic configuration. And so they have exactly the same electronic configuration. Let's take this to the and the 2 oxygen atoms will try to, firstly, there's going to be an end-to-end overlap. They're going to try and pull each other's electrons. So the first thing that will happen is there's going to be an end-to-end overlap. The 2 oxygen atoms would come together, and the orbitals that are facing each other, they're going to start to overlap. And the electrons of the 2 oxygen atoms would be stuck in the middle. Forget the green one. Look, let's focus on the red ones first. So the red orbitals, the 2py orbitals, they will overlap end to end, and the electron density would become maximum in this middle space over here. And this side would shrink because the electron would stop going to the other side. So that's going to be a lot smaller. So it's a P and P overlap, which we have already studied. So the 2 orbitals of oxygen have overlapped and they've merged together. And there's a P and P overlap, which we did discuss earlier. So that is what a P and P overlap looks like. So in the middle, right in the middle, the first bond that's formed is a sigma. It's a sigma bond. Is this clear? Is the first part clear?
Yes.
Yes.
I said, now because of that, the green orbitals, I mean, so the first one I've bonded, I mean, 2py, let's circle that. 2py has already bonded. It ended up forming a sigma bond, and it was an end-to-end overlap. That was a sigma bond. What about the 2pz? The 2pz also needs electrons. So for example, let's focus on this 2p, this 2pz. So this 2pz needs electrons. So it's going to try and pull the other oxygen's electron towards itself. This 2pz also needs electrons. It needs two electrons buzzing in this area. So it sees the other oxygen atom's electron. It's going to try and pull that electron towards itself. The end result would be the electrons would be stuck in this middle space over here because both atoms would be fighting over the same electrons. So the electrons would be, this orbital is trying to gain the other orbital's electron. This orbital over here is trying to gain this atom's electron. So the end result that's going to happen is that the two electrons in the green orbitals, the ones that are parallel to each other, they are going to get stuck in this middle space over here. And they would start to overlap sideways. There's going to be a sideways overlap of orbital, and the electrons would kind of get stuck in the middle space over here. So the electrons would be shared above and below. And there's going to be maximum electron density in this middle area over here. Same applies to this one, and that's your pi bond. So the second bond that's formed between atoms is a pi bond. Is this clear what a pi bond is and what it looks like?
Sir, a pi bond, isn't it formed between a double bond?
Yes, so now it's a double bond, right? The first bond is a sigma bond. The second one is a pi bond.
Oh, all right, all right.
I mean, this is what we discussed, that you're always going to have pi bonds when you have a double bond or a triple bond. We're going to do an example of a triple bond as well. Is that clear?
All right. Yes.
Hamza, Mani, Mikal, Rima, is this clear?
Yes, sir.
So that's what a pi bond is. So I'm going to write down the properties. So remember, the first bond is going to be an end-to-end overlap, and I'm talking between atoms, right? I mean, the atom can bond with other atoms, but between atoms, the first bond is always going to be a sigma. The rest are going to be pi, because once the middle part is occupied, that's your sigma bond. The other overlapping would either happen above or below. So the properties of a pi bond, number one, the first point about this is that it's a sideways overlap of orbitals. The second property is that the electron density does not lie on the axis between the two, like it doesn't lie between the two nucleuses. So electron density lies above and below the axis connecting the two nuclei. So connecting the two nuclei. The third thing is rotation is restricted. And I'm going to talk about restricted rotation slightly later. Rotation gets restricted because of a pi bond. What are the other properties that we wrote for sigma bonds? The other one is the same one. So those are the properties of pi bonds. Remember, it's always going to be a sideways overlap of orbitals. So we're going to do another example. Let's do the example of a triple bond. Let's say I've got N triple bond N. So how would two pi bonds look like? Although they're going to ask you to draw this one. They're not going to ask you to draw a triple bond because it's slightly harder to draw. But the concept is important. That how would a triple bond form? So the first thing is, let's look at electronic configuration of nitrogen. It's got 7 electrons, so that means it's 1s2 and 2s2, and it's 2p4. Sorry, 2p3. So that means it's 2px, 2py, and 2pz, and each one of them so each p orbital has just 1 electron. So that means the 3 p orbitals, they need electrons. So these are the orbitals that are going to take part in the bonding. The other ones are full, so we don't care about them. It's these 3 orbitals that are going to take part in bonding. Now, what's going to happen is, so remember there are 3 p orbitals now. So let me draw a nitrogen atom. So a nitrogen atom would kind of look like this. It's 2px. So let's say that's on the x-axis, and maybe let me just make them slightly, making them slightly thinner so that's the first one. The 2py would be on the y-axis. Sorry. So that's 1 electron on the y-axis. And then I have a 2pz. The 2pz is going to be on the z-axis. Imagine it coming out of the page and going into the page. So the 2pz, just a second. This one. So the 2pz, its electrons are coming towards you. So remember, each of these orbitals, each one of them has 1 electron in them. They need 2 electrons. So that's your p. That's your nitrogen atom. The other, I haven't drawn the other orbitals because I don't need to. They're already full, so they're not involved in bonding. So these are the 3 orbitals that need electrons. They already have 1 electron. They need another electron. So is this clear? Is this clear?
Yes.
So what's going to happen is that there are going to be 2 nitrogen atoms. So here's your other one. And they're going to move towards each other. They're going to try and, so the first overlapping that would happen is going to be an end-to-end overlap. They will both try to pull each other's electrons. So they're going to try and pull each other's electrons. And when they do so, what will happen is that the orbitals would start to merge and the electrons are going to get stuck in this middle space over here. So that's the first bond that's going to form. And there's going to be overlapping, and let me shade that. So the electrons are going to be stuck in this middle part, and they're going to stop going to the other side. So this side would shrink. So that side would be a lot smaller now. Same applies to this one. This one would also shrink. And that's your sigma bond that's formed. Is that clear?
Yes.
So what about the red ones? The red ones also need electrons. So they're going to try, because the red orbitals, they have 1 electron. So the red ones, they would also start to attract each other. They're going to try and gain each other's electrons. And again, they won't be able to gain them, but instead the electrons would be stuck in this middle space. So there's going to be overlapping happening, and that's going to be your pi bond. So the red orbital would overlap with the other atom's red orbital, and they're going to overlap, and let me shade that. And the electron density would be maximum in this middle space over here. So it's going to be maximum in the middle space over here. Now, the last thing is, if you look at the the PZ orbitals, they are also parallel. Now, imagine them coming out of the page and going into the page. So if you look at the, and let me draw them in a darker shade. So your PZ orbitals, think of them overlapping in front of the molecule and behind the molecule, because the z-axis is coming out of the page. So the PZ orbitals are also they're also parallel to each other. So they're going to start overlapping. They're going to try and pull each other's electrons, and the overlapping would happen in front of the molecule and also behind it, like on the z-axis. So the overlapping would also happen behind that, and there's going to be overlapping happening behind that. And let me so that is what's happening. Is this clear?
Yes. Yes.
Okay, so that's how two pi bonds are going to form. So there's a sigma bond in the middle that's an overlapping end to end. That's a sigma bond. There's a pi bond up on top and below that. That's one pi bond, and there's a pi bond that's getting formed in front of it and also behind it. So you've got two pi bonds that are getting formed, and that's your nitrogen molecule. So you've got double bonds, you've got triple bonds. Now the easy thing is you don't have to go into a lot of detail with this. Most of the questions are going to be really straightforward. Remember, the concepts are difficult, but the questions would kind of, they would tend to be very, very easy. For example, you know what a pi bond looks like, right? It just looks like an overlapping above and below. So for example, they might ask you to draw if they ask you to draw the pi bond in an ethene molecule, right? So here's your ethene molecule, and they're going to tell you to draw or sketch the pi bond. So all you have to do is draw this molecule. Where exactly is the pi bond located in this molecule? Like between
the carbons?
Between the carbon atoms, right? So all you have to do is, this one is the sigma bond. They just ask you to draw this or sketch the pi bond. So it's basically two orbitals that are parallel to each other, and those orbitals are overlapping. So this is all you have to show, and you can kind of shade it or color it. So that's about it. So questions are going to be very simple. That's all you got to do. You don't have to go into a lot of detail about figuring out what type of pi bond would be formed, which orbitals would form it. You don't have to go into that detail. If you have the structural formula in front of you, that's about it. That's pretty much it. And then they're not going to ask you to sketch two pi bonds, because it's obviously three-dimensional drawings are difficult. So they're probably never going to do that. Similarly, if you've gotten a question and they've asked you to draw, they've asked you to draw or sketch the pi bond in an HCN molecule. So tell me, where is the pi bond? Between which atoms?
CNN.
So it's between C and N. So all you have to do is draw this, and then it just asks you to sketch one of the pi bonds. So we're going to just sketch one of the pi bonds. So it's going to be an orbital of carbon and an orbital of nitrogen, and they're going to overlap above and below. And you shade it, that's about it. So questions are going to be very simple. That's about it. And there's going to be another pi bond actually over here that would be in front, like coming like the black one over here. So there's going to be that one would be coming in front of the overlapping would be happening in front of the CN and behind it. But that one obviously it's difficult to sketch. So the questions are going to be just very simple. This is all you got to draw. That's it. Is that clear?
Yes, sir.
Yes.
So then, so you've got sigma and you've got pi bonds. Now what I'm going to talk about is I'm going to talk about a rotation, like sigma bonds. That's an unrestricted rotation. I mean, this is what we talked about sigma bonds, right? That when you have, there was this point that rotation is not restricted in a sigma bond. What that means is, let's say, okay, let me talk about it at the bottom. So let's talk about the last point, which is sigma bonds have unrestricted rotation. So they have unrestricted rotation about them. So let's think of a molecule. I'm going to draw the three-dimensional shape of a molecule. I've got I'm thinking about ethane. So ethane has two carbon atoms. It's got an H. There's another H. And there's another H. So carbon makes 4 bonds. And all of them are single bonds. So what type of bonds are they?
Sigma.
Okay, so all of them are sigma bonds. Each one of them. Now think of a molecule, and this is a three-dimensional drawing. What I mean by that is that ethane model structure, just a second, let me, if I can find an ethane, like a three-dimensional structure of ethane, just a second. So this one, or maybe if that would be sufficient. So if you look over here, this is what an ethane molecule looks like, right? This is the sigma bond. All of them are sigma bonds. I'm actually more interested in the middle one, right? Now imagine this sigma bond, like think of these three as a fan. Like there's a fan that's hanging on the ceiling. So imagine that this fan can sort of spin around. Just like a normal fan does. And there's this fan over here. There are 3 bonds over here. And the atoms are attached at the end. So think of this as a fan that's spinning around. Okay, so imagine there's a sigma bond, there's a fan that's spinning over here, and there's a fan that's spinning over here. Now, even if this fan spins, the bond does not break. Because what is the bond? The bond is the force of attraction. There is shared electrons right in the middle, and this nucleus is getting attracted and this nucleus is getting attracted, right? So even if this thing spins, the attraction would still be there. The electrons shared would still be there. The nucleus of this atom would still be there. So the attraction would still be there. So imagine that this molecule, if I rotate it around, think of it like, think of the middle one. Think of this as a sigma bond, and there are two fans that are hanging from that sigma bond, one on top and one at the bottom. And let's focus on the bottom one. So I'm saying that if this thing kind of spins around, right, nothing would happen to the sigma bond, because the sigma bond is a force of attraction. There's shared electrons. Even if this thing is spinning, the nucleus would still be attracted to the shared electrons. Is this point clear? Do you get this point?
Yes.
Is this clear to everyone, Rima? Is this clear?
Yes.
So always imagine these molecules, because we have, the problem with us is that we've always seen molecules as these rigid molecules. The molecules are not rigid. They're like, most of them are like fans. They're all spinning around. The top part would also rotate. It can also spin around like a fan. So think of these two fans that are spinning around. The bond in the middle would be unchanged. It's shared electrons. This nucleus would be attracted. This nucleus would be attracted. It doesn't matter where the other bonds are pointing to. The nucleus would still be attracted. It's just like your ceiling fan, like the fan hanging from the top. It doesn't matter where the blades rotate or how they rotate. It's still stuck to the ceiling, right? So it doesn't really matter where these things are pointing, how this thing is rotating. It's still stuck to the sigma bond. The force of attraction is still there. So hopefully this point would be clear to everyone, right?
Yes, so I have a question though.
Yes.
If, for example, the bottom CH bond, yeah, is going clockwise, would the top one also go clockwise, or can I go anti-clockwise?
No, they can go anywhere they want to.
Okay, so it's like
It's
unrestricted. They can spin anyway.
Yeah, it's like unrestricted. Like, I mean, they're all bumping into other molecules, right? So think of
like if one's going one direction, can the other one go in a different direction?
Yeah, it's like they can just randomly go around anywhere, right?
Okay.
So from now on, don't think of
I'm
molecules.
sure they don't break, yeah?
The other bonds,
Yeah.
they're not going to break. This is what I'm telling you, that imagine this thing rotating, right? But what is the bond? It's these. I mean, there's this overlapping happening, right? There are two electrons that are stuck over here. Like if I just so is there anything happening to the force of attraction? It's the shared electron. The carbon has this nucleus, right? So the force of attraction is still there, right? The electrons are being shared over here in the middle. They're stuck in the middle. And the nucleus is still getting attracted to those electrons, right? So the force of attraction is still there. So it doesn't really matter how this spins around. The nucleus is still there and the electrons are still there. Is that clear?
All right. Yes.
So from now on, imagine these molecules as not being rigid molecules. Like don't think of them as like the bonds are stuck in space. Think of them as something that is constantly spinning around. And the sigma bond will not stop that. But on the other hand, if you have a double bond, the double bond will do that. And here's the example. Now imagine the same thing, and this time you've got a double bond. So when so let's do the example of ethene. So if there was a single bond, rotation would still be possible, right? So one second. So I'm taking the example of ethene. So if there's a single bond, there's going to be unrestricted rotation. I mean, this thing can just spin around wherever it wants to go. Like I mean, think of this as something that's spinning at the bottom, right? But in ethene, you've got a double bond. What that means is you've got a double bond. So there's there's a p orbital, there's another p orbital, and there's going to be a sideways overlap of orbitals. They're going to overlap here. And they're going to overlap over here as well. So there's going to be overlapping of electrons that's going to happen on either side. I mean, that's how, I mean, like if I just show you, this is exactly what we drew earlier. Like I've just turned it vertical, but that's exactly what we did earlier. Is that clear?
Yes.
I said, now the thing is, now there's not going to be any independent rotation. Like if this thing rotates, the other side would have to rotate with it, because now they're stuck in place, because I can't rotate this carbon independently, because this carbon is kind of connected with this carbon now. Because if I just rotate this side, this overlapping would break. So now that's not possible, because they've formed bonds above and below. So you can't just twist around one side and expect the other side to stay in its position. Now the thing is that if you rotate one side, the other side would also rotate with it. I mean, an example for that is this one. Like so pi bonding happens. So pi bonding happens in this way, that there's overlapping above and below. So I can't rotate this side independently, because the pi bond would have to break. The alignment will break if I just rotate this side. Is this point clear?
Yes.
Yes.
Okay, so now there is no unrestricted rotation. Like, I mean, I can't just twist one side, like turn it around, turn one side and expect the other side to stay wherever it is, right? That's not going to happen because of the overlapping that's happening above and below, because the pi bond would have to break otherwise. So now unrestricted rotation is not possible. The two sides are locked in position. And now the molecule is rigid. It can't move. Like if this bond is pointing over here and this bond is pointing over here, so they're stuck in place. They're completely aligned. They can't change their alignment. Over here, the molecule, I mean, this side was rotating freely like a fan. This side was rotating freely like a fan, and they were randomly moving around. Now that's not possible. Now that's a very rigid molecule with a very well-defined bond orientation. And if this bond is pointing here, this bond would be pointing here. I can't twist one side and point the bonds in another direction. I can't do that. So no unrestricted rotation, or we can say rotation is restricted. So rotation is restricted due to pi bonds. Due to pi bonds. Is that clear?
Yes.
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 I said, now the reason I'm stressing on this is
So
because
sir, this molecule won't move at all, yeah?
yeah, because I mean, you can say that if you try to twist this side, like you try to rotate this side, the other side would also rotate with it. I mean, there's no independent rotation possible now. Like over here, this fan was spinning randomly, and this fan was spinning randomly. They were free to spin in any direction they wanted to, right? But now the thing is that if I pick the molecule from the bottom and try to rotate it, the top part would also rotate with it. Is that clear?
Yes.
So the reason I'm stressing on this is because when you study organic chemistry later, this rotation getting restricted has a lot of, I mean, it has a lot of applications, especially when it comes to isomerism. Because if I have a single bond, right? So I'll just give you an idea. Whenever you see these single bonds, so imagine like if there's a Cl and there's an F. So it doesn't really matter where the Cl points. Like the Cl could point downwards, because this fan over here is spinning in whatever direction it wants to, right? So the CL might sometimes point downwards. It might sometimes point upwards. Is that clear?
Yes.
Yes.
But if the same molecule has a double bond, like a different molecule has a double bond, now the problem would be that the direction of the bonds will matter because the bonds are stuck in their position. Like if the CL if this CL is pointing downwards and this CL is pointing downwards, rotation cannot be possible around a pi bond. So if I twist this side, that side would also, so the CLs would always be pointing in the downward direction. They can't just independently point in any random direction. So we'll talk about that later on, but hopefully when we study organic chemistry, but hopefully this point is clear. TK, is this clear? No questions, right? And we're out of time as well. Is this clear?
Yes.
Yeah.
Yes. So, sir, just to confirm, so a double bond,
Yeah.
a molecule with a double bond, it can move independently. So my question is, can it move? Like, can the whole thing move?
I mean, the whole thing can
Or
obviously.
not at all.
Just very quickly. So the whole thing can obviously move.
Like this just goes in clockwise.
No, the whole thing, like if I pick this molecule from this side and I twist it, the whole molecule will get twisted. Like it's going to flip. The whole molecule will flip. Do you get my point?
Oh, all right. Yeah. So it does move.
But obviously it can move around. You can sort of pick it up and put it in another direction, but the bonds are locked in position. Like you can't sort of independently twist this side only. Do you get my point?
All right. Yes.
Over here, this side can independently be twisted around, but now that's not possible.
Yes, I see. All right. Thank you.
Then TK, let's continue next time then, TK. We'll do hybridization next class. Okay, take care. Office.
Okay, sir.
Bye. Thank you.
Okay.